Hello, today we're going to measure some of the operational parameters and efficiency of this USB charger I got from Amazon last year. And I'm also going to play with this new watt meter, a Peacefair PZEM-020 I got from Banggood and received it just a few days ago in the mail. It's spec'd to handle 0 to 10 amps and 80 to 260 volts. I've already played with it, and it will work down to 50 volts and up to 280 without an issue, at least at low currents. Anyway, so this charger, like many chargers, is specified. Well, let me zoom out here and get this whole thing in. Okay, so the charger is actually specified to run from 100 to 240 volts AC, 50 to 60 hertz, drawing a maximum of 300 milliamps. And it outputs 5 volts at up to 2.4 amps. So the power here in the US, at least at my house, is 120 volts, 60 hertz. I don't have a way to do 50 hertz, but I certainly can vary the voltage. And so what I'm going to do to vary the voltage is I'm going to use an Autotransformer, an old Powerstat that I've had for well over 30 years. And then I'm going to use this Toroid isolation transformer. It's a medical grade isolation transformer I purchased from eBay last year. And it can be configured as a step up or step down transformer. And I've currently got it configured as a step up transformer. So I'm using the Autotransformer on the input side, and then the output side is going into the Peacefair watt meter. The output of the Peacefair watt meter will run the USB power adapter. Then the output of the USB power adapter I'll hook up a Ruideng UM25C USB tester that monitors voltage, current, and power. And then I have a Ruideng HD35 variable constant current USB load. So what are we going to test? I want to test the input voltage, input current, power in, power factor, output volt into the adapter, the output voltage, output current, power out. And then we're going to calculate a couple values here. I'm interested in the efficiency, which is the power out divided by the power in. And I'm also interested in the power dissipation, which is the power in minus the power out. And the power dissipation is important because that's going to that power is dissipated by the power adapter and will heat it up. And you really don't want that to happen. Again, but if this was 100% efficient, it wouldn't dissipate any power. So anyway, so let's look at the setup here. Let's zoom out. There's the Ruideng. So let's plug in the power adapter. And we can see now with the power adapter plugged in that it's showing 0 power dissipated, and it's drawing less than a milliamp at 64 volts. Let's go up to the high end just to see here. Here's 240 volts. This is the high end of what it's spec to handle, and again, it's drawing less than a milliamp. So it's very efficient when there's nothing plugged into it. I mean, it's drawing almost no power. So now let's plug in this Ruideng power meter here. And zoom out. Move this up a little bit. I see. Did I kill it? That would not be good. Let's see if this is doing anything. Oh, well, hold on. I had the switch turned off. Works better when you turn the power on. Okay. So let's take this out again and let's see what this thing is drawing. Okay, so it's essentially drawing no power without the Ruideng power plugged in. So let's plug in the Ruideng. And let's turn this down to... Oh, I went below. It's only spec'd down to 100 volts. There, at about... Okay, so there, 90 volts, 93 volts, it's drawing 7 milliamps. And that's just the power that this USB adapter is drawing. And so in the end, we may need to, if we do some calculations, we could factor that out. So right now, I'll take this down, 93 volts in. 7 MA. Power factor doesn't register. V out's 5.09. I out is 0, P out is 0. Now let's go up to the high end. Here, I just want to see, well no, let's go to 120. Here, let's get an idea of how much the Ruideng is drawing, so we can correct our measurements later here. Okay, so at 120 volts, we're getting 6 milliamps, and we're still putting out 5.09 volts. Now let's go up to let's go to 220. Just for the, let's go to 240. Again, I'm just varying the Autotransformer. Okay. So here now we're at 5.12 volts out. So the output voltage is slightly sensitive to what's coming in. Actually call it 5.15 at 240 volts and 5 milliamps. And so this thing's not registering any power because I don't think there's enough power for it to see. But it's obviously, we've doubled the voltage and the current draw hasn't changed. So it's going to be dissipating a little bit more power, but we don't know because of the power factor. Okay, so there's some base measurements. Let's come back down to 120. And now let's add the load. Let's move this out so we can. Let's see if we can get a better focus on this. There we go. Okay. So now it's just the power factor's coming and going because the extra load here. So let's turn this load on. And right now, let's start at 2.4. Let's put it up to 2.4 amps, which is the specified output. Of this part. Okay. So let's start down here. Oops, I went too low and the power supply shut down. Okay, so interestingly enough, no, it doesn't like that. Let's go back up to 100 volts, see if it works at 100 volts. Okay, it's working at 100 volts, as 97. It's a little below its spec. Let's turn it up. So at 100 volts in, we're drawing 2.33 amps. The power is 1.52 watts. Power factor is 0.65. The output voltage is 5.09 at 2.4 amps. And we're dissipating 12.24 watts. Or we're outputting 12.24 watts. Wait, is that right? Oh yeah, so I have 15.2 watts in and 12.24 watts out. So how much power is this thing dissipating? Let's bring in the calculator. So this is $15.2 minus 12.2 clear. Let's try this again. 15.2 minus 12.2 clear. 15.2 minus 12.2 equals 3 watts. Yeah, okay. 3 watts. So this thing should be getting warm. I don't feel it yet. And let's see what the efficiency is. The efficiency is going to be I bumped something there. 12.24 divided by 15.2, 80%. Not bad. This is at 100 volts. So let's go up to 120. So now at 120 volts, we're drawing 2.00 amps. Okay, less current for the same power output because we've got a higher voltage now. That makes sense. Power in is exactly 15 watts. Power factor is 0.62. That got a little worse. V out is 5.11. I out, still 2.4 amps. P out is 12.24 watts. 12.24 watts. Okay. So I'm not going to calculate this at each point. We'll make some measurements, and then I'm actually going to put it into Excel and put a link to the measurements when we're done. This was just more to show how to do this than to go through a whole set of tedious measurements. So now we're at 141. Yeah, let's turn that down. $140 volts. We're now at 174 milliamps. So this was 200 milliamps before, and 233 milliamps. I screwed up there. That's all right. The input power, according to this, is 15 watts. Power factor is a 0.61. Output voltage is 5.11. Still 2.4 amps. This constant current load is working very well. And we're at 2.4. And P out is 12.26 watts. Okay. Let's go up to, let's try about 176. This isn't a normal voltage, just kind of a midpoint here. Oops, did I bump this? Let me refocus this just to make sure everything's in focus. So we're at 172 volts. We have 141 milliamps, 15.1 watts, power factor 0.62, V out is 5.11, 2.4 amps, 12.28 watts. Let's go up to 220. Let's go up to 200. Okay. So now here at 201 volts, we have 123 milliamps in, 15.2 watts. So this thing's keeping remarkably constant power dissipation over a very wide voltage range, which means it's a good design. 0.62 power factor is not changing much. Hold on, this segment's about to end. I'm going to have to restart it. I only get fixed segments with this camera. Okay, so now Back here, again, we're at 5.11. I'll call it 5.12, 2.4 amps, 12.29. The output's holding remarkably steady over a huge voltage range. So this is a good, I am actually pretty impressed with it. So, although just because this one's working good doesn't mean they all do. This is one sample. In general, you want at least 5 for a statistical sample, and better at least a dozen. So, you know, when you see tests on the internet and somebody tests one of something, doesn't mean anything, except that that one did something. You really need to test a whole bunch of them and get a distribution. 5's like the minimum of anything you'd really like to test. Anyway, so here we're at 219 volts, 111 milliamps, 15.3 watts, power factor 0.63, output 5.12. This thing's remarkably steady, 2.4 amps out. 12.29 watts. Let's go up to 240 volts, which is the top end of what it's spec'd for, I do believe. Yes, 240 volts is the top end of what it's spec'd for. So now at 240 volts, we're at 106 milliamps. 15.5 watts, power factor 0.61, 5.12 out, 2.4 amps, and then, yeah, 12.3 watts. So that's pretty amazing that it held very steady at full output over that entire voltage range. That means it's actually a pretty good little power supply. Let's go down now to, let's come back up here to 240 volts. And let's drop it to an amp and see what it does. Let's turn the current down to an amp. Okay, so I went down to an amp, 5.126 volts, output barely changed. So let's take this data down, 241 volts. We've got 52 milliamps in. We're dissipating 7.16 watts in. Power factor 0.56. It's come down now that we've lowered the current. Output 5.125, we'll call it 5.13. At 1 amp. And we're dissipating 5.22 watts. Let's see if this thing's getting warm. Yeah, it's starting to get warm. Okay, that's not surprising. It's dissipating a few watts. Let's come down to 120 Okay, so here we're at 120 volts. The input current is now 83 milliamps. It went up from the 240, but that makes sense because we dropped the voltage. To get the same power, we need more current. We're at 6.58 watts in, so it's drawing a little less power. 0.65, a much better power factor now. We're getting 5.12 out, 5.12 volts out, 1 amp, and the output power is 5.22 watts. Let's go down to 100 volts. Yeah, I can't hit it. There we go. Okay, 101 volts, 100 milliamps. 6.53 watts. Power factor 0.64. V out 5.12. It's incredibly steady. I'm very impressed with this little power supply. P out is 5.22. Now let's go down to 90 volts just for the hell of it. It's still working. 90 volts. 113 milliamps, 6.51 watts, power factor 0.63, 5.12 volts, 1 amp, 5.22 watts out. Anyway, so here's the data we've taken so far. Let me zoom out here so we can see it. Anyway, let me focus here. Okay, so I'm going to enter this in on an Excel spreadsheet and plot it out and put it in a link. Anyway, so I hope you learned a bit about how to measure the efficiency of a little USB power adapter. Again, if you just wanted to measure it over your own power range, you wouldn't need this transformer. You could just use the Autotransformer and go straight into it to adjust the voltage up and down. But I needed the step-up transformer to get the whole power range, since up to did its spec for. So again, this little Banggood watt meter, I'm very impressed with it. It was like 10 bucks, 12 bucks. I forget, it was incredibly cheap. I just hooked it up temporarily like this. I'm going to build it into a case now that I see that it's nice. I wanted to try it out before I put the effort into building it into something, but no, I'm very impressed. I like it. It's much better than the old one I had. And these little Ruideng adapters are very nice too. Anyway, thank you for watching. If you like this and would like to see more like this, please hit subscribe. I will be doing more. Thank you very much.